Hey everyone, and welcome. Today we're kicking things off with our very first topic, an introduction to EEE 3027, Communication Engineering. In this explainer, we're going to explore the absolutely incredible journey of data. We'll figure out exactly how a simple thought, a spoken word, or a single pixel travels across the globe, literally in the blink of an eye. Here is our roadmap for today. We'll cover the communication process, layered networks, guided media, the big fiber versus coaxial showdown, the wireless spectrum, and finally, the father of information theory. All right, Section 1, the communication process, the big picture of data travel. Now, if you just have one person talking directly to one other person, communication is pretty simple. But, well, that's just not the world we live in, is it? A true communication system is all about allowing a multiplicity of terminals to reliably and efficiently share the exact same physical space. The real magic of modern systems, like the internet or those massive cellular networks, is that millions of users are talking all at once without colliding into each other. Think of it as the ultimate hero's journey for a single data packet. It starts at the information source. The data enters the network and control layers, which prep it for the transmitter. Then the transmitter sends it through the channel. Now, that could be a physical cable or just the open air. After that, the receiver grabs it, passes it back through the network layers on the other side, and finally delivers it safely to the information sink. Every single text message you send takes this exact journey. It's wild. Moving right along, Section 2. Systems and layered networks, organizing the invisible traffic. Remember those network and control layers we just mentioned? They're essentially the ultimate traffic cops. Without them, having millions of transmitters and receivers trying to share the same physical medium would be complete chaos, just absolute gridlock. These abstraction layers enforce the rules and keep these massive systems running flawlessly. And they actually function a lot like a bustling, multi-level factory. Take the 7-layer OSI model, for example. Your data starts at the application layer at the very top and then works its way down an assembly line through presentation, session, transport, network, and link layers until it finally hits the physical medium at the bottom. And across the gap, peer protocols ensure that the receiving factory knows exactly how to unpack it all. When we build this into physical hardware, there's this really beautiful mirror-like symmetry to it. A radio transmitter packs up the information, pushing it through the protocol stack, modulating it, upconverting it, amplifying it, and shooting it right out of the antenna. Then the receiver catches it and does the exact sequence in reverse. It amplifies, downconverts, demodulates, and sends it back up the protocol stack. It's just a perfect engineering mirror. Okay, Section 3, guided transmission media, wires, cables, and physical pathways. So let's look at a map of these physical pathways. Transmission media basically forks into two major roads: guided, which means wired cables, and unguided, which refers to wireless airwaves. For this part, we're going to focus purely on the guided, wired side of the family. And right off the bat, we have to give a brief, respectful nod to the humble, twisted pair cable. You've definitely seen this before. It consists of two conductors, each with an insulator twisted around each other. Simple, right? But for decades, this was the classic workhorse of telephone lines, reliably providing voice and data channels across the entire globe. Let's step it up. Section 4, fiber-optic versus coaxial, the heavyweight cable matchup. In one corner, representing the old guard, we have coaxial cable. Structurally, it's a solid inner conductor wrapped in an insulator, then a metallic shield, and finally a plastic cover. It's tough and it's reliable. It was widely used in analog networks where a single cable could carry 10,000 voice signals, and later on in digital networks carrying up to 600 megabits per second. But in the other corner is the glowing, futuristic champion, fiber-optic cable. Coaxial's metallic limitations, topping out around that 600 megabit mark, just can't compete anymore. Fiber optics use a core made of glass or plastic to guide actual light. It offers truly massive bandwidth and is highly cost-effective. And that's exactly why it has largely replaced coaxial as the absolute standard in our network backbones today. To put this upgrade into perspective, think about this number, 1,600. That is 1,600 gigabits per second. Using advanced techniques like wavelength division multiplexing, which, simply put, is sending multiple different colored lights down the same tube at once, fiber optics unlock these jaw-dropping data transfer rates. We literally went from 600 megabits on coax to thousands of gigabits on fiber. It's a real game changer. And the way this works is practically magic. A sender shoots light into the glass core, and because it's surrounded by a less dense cladding, the light waves bounce perfectly off the edges. They just zigzag right down the channel. This allows data to travel immense distances, quite literally at the speed of light. Moving on to Section 5, the wireless spectrum, floating into the unguided airwaves. Now, when we cut the cables and send data invisibly through the air, it actually interacts with the very shape of the Earth depending entirely on its frequency. Below 2 MHz, signals use ground propagation, literally hugging the curvature of the planet. Between 2 and 30 MHz, they bounce off the ionosphere in what's called sky propagation. And above 30 MHz, we rely on direct line-of-sight propagation between antennas. Let's break these wireless waves down a bit. Radio waves are lower frequency and can easily penetrate walls, which makes them perfect for, say, your car's AM radio. Microwaves operating up to 300 GHz require a line of sight, which is why your cellular networks use them to talk to the nearest tower. And finally, infrared operates at massive frequencies but absolutely cannot penetrate walls, keeping it strictly for short-range stuff. Think of your TV remote. To ground this in reality, just think about a classic omnidirectional radio antenna. Because radio waves radiate outward in all directions and have that wall-penetrating superpower we just talked about, it is exactly the reason why you can sit deep inside a solid concrete building and still clearly listen to an AM radio broadcast. Finally, Section 6, Father of Information Theory, the mathematical bedrock. Let's take a moment to meet Claude Shannon. He is universally recognized as the father of information theory. The papers he published in the late 1940s and 50s were so profoundly seminal. They didn't just advance communication engineering. Honestly, they effectively created the entire field from scratch. Back in 1948, Shannon published a paper with this exact title, A Mathematical Theory of Communication. It is not an exaggeration to say that this single document laid down the foundational mathematical laws of digital communication. It governs literally every piece of technology we've talked about today. Which leaves us with this final provocative thought. How exactly does a mathematical theory written on a piece of paper in 1948 make the modern 5G smartphone sitting in your pocket right now entirely possible? Well, that is exactly the exciting mystery we're going to unravel over the rest of this course. Thank you so much for joining me for this explainer, and I can't wait to see you in the next one.